and then I'll tell you exactly how that relates to what it is we're doing. I'm going to get abstract on you guys now. What did you think I said?
No, I can't hear.
Oh, abstract. I'm going to get abstract. So I'm going to use symbols and my generic function again. I think we might be on 14. Where will we leave off? 14. That's a tangent plane, right?
Yeah.
Now we're on 14.5. All right, so we have a function f of xy, and then I'm going to draw a curve in 2 dimensions. And let's say that that curve in 2 dimensions is written as in parametric form. So we'll look at this parametric curve. And the curve that I drew on that computer program was a circle. It doesn't have to be a circle. It could be anything. And then I put little arrows here to show you that this has a specific direction that it goes. But that's, again, not that big of a deal. So what is important, though, is that I'm going to project that up on the surface. And now, being projected on the surface, who knows how it'll look like, but if we look at it from the top, should be the same shadow image of that 2-dimensional picture. But up in space, it could look whatever. So now the question is, how can we express this curve? I don't want to call it R of t again. No, I know what. Let's call it capital R of t. That's not very. Now, what's capital R of t going to equal to? And that, I'm now in space, so I'll have 3 components.
X, T, Y, T, C, F, X.
Wait. Yeah, what does that equal? Somebody was saying it. F of x, t, y, t, right? What if I write it as f of r of t? Oh, what's all this? Ooh, ooh. Well, what do you think of in math when you see something like this? F is a function, R is a function. What do you think of? There's a special math word for this. What? Composition. Is it going to work? Let's see. R of t, what's R of t? So R, what does R take as an input? As an input. So R takes a single value as an input, and then it brings it, this particular little r at least, goes to 2 dimensions. So we can write those vector valued functions that we were studying back in chapter 13 now in function notation like this, where it goes from R to R2. Now the composition, now that we have this composition, the f of r of t is a combination of these two functions. One function is inside of the other, right? And so now, if we look at this composition f of r of t, what's the bottom line function input for this? R2 or R? R. So it takes in a t value, right? And then where is this t value going to go? It's going to go to R2, right? So the R2 is going to input your x and y values. And then now, that's the R itself. R goes from R to R2. And then now, when you put that R2 into the f function, where is it eventually going to go? Back to R. It's going to give you a real number, right? So this is going to be back to R, which we'll just represent as Z.
So we're taking a t, and when we plug it in, we get an x, y out, and then plugging those x, y's into the R
F into the f function,
and then we get a z.
and then you get a Z out, yes. So your R of t is the innermost function, and then your outer function is your f function. So this eventually goes from t to z, and that is what we have written up here. T is the input, and z is your output. Right? Okay. So that was the pre-calculus part. Now, what else was in my program, in that animation that you saw? The tangent vector, right? So tangent vector. So we're going to probably be interested in the derivative of this. So let's jump to this idea of the derivative. So the derivative, we'll call it capital R prime of t, seems to be pretty straightforward. So how do you take derivatives of compositions? Chain rule, right? So let's look at the chain rule idea for this. Martha said f prime, right? But there are two sets of derivatives for this function.
There's f and y. So if you do fx times the x part of the parametric equals 1, and then you add that to fy times the y component of the parametric 1, then I think it would work. You figure out
We're not going there yet, but yes.
That makes sense.
So you have to.
Just
No, right now, first, just say we're wrong. First, we're just saying R is not prime of t though, so there's no actual values, right? So that would.
xt what?
In fx times that dx in t, we have plus fy dy
Is that this part, or is that the whole thing?
Yeah, I think that covers it, I think. Yeah, I think so. 'Cause we have the derivative of r prime in there. It's there.
Where's the derivative of r prime?
It's in there. I don't know. I think it's okay, but we have to prove it somehow.
What?
So my little brother's doing right now, kind of real analysis.
We have to find a way to prove it.
Wow. So this expression here doesn't quite, it's weird. This is a vector. R prime of t is a vector, right?
Are we scalable for them? Because
So this is a scalar, I wonder. So this is the thing that's in question. So this f prime, because of the fact that there are two variables for f prime doesn't make sense. Okay? But it is a derivative, and it is some sort of derivative. Now, Martha blurted out the gradient. Oh, yeah. So, if you isolate these two components, they actually make up what we call the gradient. And this isn't exactly the way I wanted to define the gradient, but we can now take a look at the gradient. The gradient of f is defined to be a vector. So f, remember, is f is a function, a scalar function. And when I mean scalar function, I mean the output is a scalar. F is a scalar function that goes from R2 to R. And the gradient of f, first of all, the notation for the gradient, it's an upside down triangle. And then I have the f next to it. And this is actually defined as a vector. And the vector is the partial of f with respect to x and the partial of f with respect to y, or fx comma fy, or you can put the I and j if you want. But we see that there's a gradient component there. We also see that there's an r prime component here as well. So by looking at the gradient and the r prime components, can you see what actually, how to write this derivative? This is dot product. All right, so we'll put this on the next page. All right, now we're dealing with partial derivatives, right? But what we need to know is we need to know what kind of derivative are we taking here. We're taking the derivative with respect to x or y or t or f or r. What are we taking the derivative with respect to? T. Now there's only one variable, t, here, right? So this is a straight derivative d. And we'll try to clarify this a little bit later. So what we found that the derivative of this composition is the gradient dotted as a dot product with the derivative of the inside. So the derivative of the outside, if we want to look at it as a derivative, because it's a function of two variables, would have two components. And then if we follow the chain rule idea, it looks just like the chain rule, except now we're dealing with higher number of inputs. Dan?
Gradient is like the slope, or gradient is like the slope of the function?
No, it's the gradient is a way to collect all the partial derivatives into one thing, and the thing happens to be a vector. All right, so this kind of breaks down to let me use the partial symbols. So notice where there's a curly d, the partial d versus a regular d. And so if we look at the different pieces of it, it just boils down to this. Now in Calc 1, they wrote something like this for the chain rule, and then they proceeded to cancel the dx, something, because you couldn't do it back then either. Technically, that whole idea of canceling is that you can't do it because Leibniz notation is just a notation that says that you're taking the derivative with respect to whatever variable. It's a notational abuse. Yeah. So when you get to the higher level of like your functions that are functions of more than one variable, now that notational abuse would actually get you something that would actually be incorrect or would not work out. Sam?
I have a question. So I was thinking when you brought up the picture of the function, and I was thinking about how the hand plane was 0, but it wasn't exactly a min or a max. I thought about optimization problems and how you said equal, like you could set the cardinal equal to 0.
Mm-hmm.
To get a flat tangent plane, and that might be a min or a max, but in Calc 1 and 2, when we wanted to test whether it actually was min or max, we did the second derivative. But how would we do the second derivative of this? I'm not really sure.
Yeah.
That's confusing now. Taking the second derivative, I don't know.
Yeah, we'll save the second derivative for a couple of lectures from now.
Okay.
Yeah.
But would it be? Can you still do that? Like
Oh yeah.
optimization, like
Yeah. We're still going to do a second derivative, but the idea of a second derivative is a lot more complicated when we're in a multi-dimensional, multivariable. And so we'll
I'm sort of lost as to how you would get it.
yeah, we'll establish some ideas, and what we'll do is we'll just look at the formula that they gave us, and then if you want to dig deeper, then you can try to find like second order Taylor polynomials in multivariable.
like, so taking the idea of a tangent plane, but to a quadratic level,
like tangent parabolas. We've had tangent parabolas in Taylor polynomials.
So like, because this next order, you use the first order Taylor approximation to get the first one, and then you would take the second. If you added more, you would have the second order would be like.
Yeah, let's.
I have to think about that.
Yeah, let's not worry about that for now. That's like I said. That's probably coming on Wednesday. It's probably coming on Wednesday. All right. So it turns out that there's a nice. The book plugs this a lot too. There's a nice map tree that you can generate to help us figure out the sequence of things to add or to multiply or to subtract or whatever. And that is to build a tree. And when you build a tree, you start off with the outermost function, and you say f. And then now you ask, what is f? F is a function of what? And then you list down its number of variables below it. So we could say f is a function of two variables, right? So f is a function of x and y. So we can list down the two variables here. And then now, what are y and x and y a function of? Function of t. So at this point, you can choose one t to represent the one thing to go into, or some people write this as a t going down like this. Which one would you rather see? The diamond one? That looks a little cooler. We could say y is a function of t, and it's the same variable for both of them.
If you had different variables for, like, say, x and t, y and s, would you just write s and t and then s, like, for each?
Yeah. We'll see that.
Branch. Okay.
Yeah, we'll see that also. We'll do a few more variations of this. So anyways, you come up with this tree, and then you notice, first of all, that the bottom line here is that there's only one variable. So we know that this is going to be a straight derivative. Okay? And then the next thing we try to find is how many how many ways are there to get to this from the top to the bottom, from the outer function to the innermost variable. And you say, it looks like there's two paths to get there. So we follow the path and we say f is a function of two variables. So the one path is going to take us from f with respect to x, and since f is it's a function of two variables, then we're going to use the curly d's, the partial d's. And then we notice down here that x is a function of only one variable, so we use our straight d from the x to the t. And the same is going to happen for the y. So if there's a z, then we would just tack on another one over here. Yep. And so you take these components, the paths to get there would be df, dx, and dx, dt, and that takes you from f to t. And then there's another path, and we just add the other path, df, dy, dy, dt.
So you just add all paths.
And then you add all the paths together. So that's a nice visual way of trying to figure out what's involved in your chain rule when you have multiple variables like this. Okay? So let's do that example, that one drawing that we saw earlier. So we have our saddle, our hyperbolic paraboloid, x squared minus y squared. And then we have our circle, right? So our capital R of t is equal to cosine of t, sine of t. And then here in this particular example, it's easy enough to plug those in there. But I'm going to keep it like this, f of r of t. Now, to find our derivative, just a matter of taking the derivatives of each of these components. But now, when we get to this one, this is where we actually want to compute this derivative of the composition. All right, like I said, we could probably have just put in the cosine t and sine t for x and y and then find an easy derivative. But if this was a lot more complicated, then you may want to do it this way using the chain rule. So this is a chain rule. We need a few things before we can get started. We need f dx, partials. And so the partial of f with respect to x is 2x. We need df dy. That's the partial of f with respect to y. It looks like it's a negative 2y. We're going to need dx dt, straight d's this time. And that's, we already found that. That's negative sine t. And then dy dt is positive cosine t. So we simply put those together. We got 2x times minus sine t plus 2y times cosine t negative.
In this instance, when we're solving for that last, the t's on the inside would be the same as the t's that go into negative sine of t and cosine of t on the other part, right?
Yeah. But we do, since we want our function to be eventually a function of t, we'll use the x and y, the original x and y, to replace the x's and y's that we have here. So 2, and x was cosine t. And then minus 2, and then y is equal to sine t. And then the rest of them would follow. Okay, so now we have our derivative. I suppose we can simplify this, right? Negative 4. So that's your derivative. At least that's a z component of your derivative. But this is where we use a chain rule. Okay? So that was just a nice way to motivate the chain rules with the picture and the whole idea of the composition. We can use this with a little bit more complicated compositions of functions, and so we'll take a look at that next. Any questions, first of all? By the way, had you just composed it, this is the composition of the f function and the r of t function, right? So this says to put in my x value and put in my y value, and it becomes this. And then if you were to take the derivative of this, z prime of t, this is equal to 2 cosine t, derivative of cosine is negative sine, minus 2 sine t cosine t, which is exactly the answer that we got. So like I said, sometimes it's easy to do the composition and then take the derivative, but sometimes if your function gets a little bit more difficult or a little bit more complicated, then the chain rule might look a lot easier. Pick your battles. Okay? Questions? All right. So let's step it up with a chain rule a little bit. So let's start with an f function again. And then let's say x and y now are not regular functions. Instead, maybe they're functions of two variables. So let's take maybe as an example, let's say f of xy is equal to x cubed minus 2x squared y plus y to the fourth. And let's say x is equal to r cosine theta, y is equal to r sine theta. Kind of looks polar, huh?
Yeah.
So let's say this is your relationship between x and y. And then now I want to take the derivative of f with respect to theta, or with respect to r. We have 6. Well, let's stop and do the tree. Let's do the tree. What's our topmost function? F. So let's start with the topmost function, f. F is a function of how many variables? X and y. So f is a function of x and y. Now x and y are functions of how many variables? 2 each, r and theta. So let's do it like this. Check this out. Whoa. Does that look confusing? So this is where it might have been good to do the other approach where each of these would be functions of r and theta. But we already committed to this. We didn't commit to this. You could do it any way you want. So one thing we want to note is that there's 2 variables in the bottom. So whenever we want the derivative of f with respect to one of these 2 variables, let's say r, then are we using a straight d or a partial d? Partial d, right? So we're doing partial d's for this. Because in the end, they're eventually functions of two variables. So whenever you want to do a function of two variables, it's a partial. All right, so let's highlight. Oh, I got a highlighter. That's not a highlighter. That was an eraser. Let's highlight. What are we highlighting? R. We want the. Is it highlighting? So we're highlighting where we start and where we end. We're always going to start with F, but since now we have two variables in the bottom, it's a question of where we're going to end up. And so we want all the paths that lead to R. So we need a path from F to X, and F is a function of two variables. And so we're going to need partials for that. Now X to R, X is also a function of two variables. And that's the partial of X with respect to R in this case. So that's one path. And then we have another path that goes through Y. And so to get that other path, we label our partials. And then we put them together and we have our chain rule formula. So it's the partial of F with respect to X times the partial of X with respect to R plus the partial of F with respect to Y times the partial of Y with respect to R. You guys getting good at drawing these partials? If you don't want to, you can just say Fx and Xr plus Fy and Yr. It's the same, right?
And then you can do the same for theta.
Yeah, you can do the same for theta. So let's find those little bits and pieces. So Fx, the derivative of this with respect to x, this looks like it's going to be 3x squared minus 4xy plus 0. Fy is 0, 2x squared plus q. All right? So those are the two components. And then for each of these, we're going to find the derivative of x with respect to r. We're going dr for this one. So what's the derivative of this with respect to r? Cosine of theta, right? R is the variable. Cosine of theta is a constant. So treat it like it's 5. R times 5, the derivative of that is just 5. And then x, or so this is y sub r. Is sine theta. All right? So let's just put those together. So partial of f with respect to r is actually equal to the partial of f with respect to x. That's 3x squared minus 4xy times cosine of theta plus the partial of f with respect to y. That's a negative 2x squared plus 4y cubed times the sine of theta. Okay? All right. Well, I think in this case, I would probably leave it like this. In your homework assignments, I think they're flexible. You don't, technically, you want it all under the same level variables. Like the last level variable here is r and theta. So technically, we should put in x is equal to r cosine theta, y is equal to r sine theta, so that everything would be r's and thetas. But I think in the textbook, they're allowing you to leave your answers in different levels of variables. So we could leave this with the x and then leave the thetas as r's and thetas. In a test situation, I might just ask you to leave it like that. In a more realistic or applied situation, you would most likely be evaluating this at a specific point, in which case it might actually be a little bit easier to deal with. Because then you would evaluate this at a specific point, and then so you're going to get values here instead of horrible looking expressions. Theta, if you were going to plug in a particular value, the r and theta would be given, and then when the r and theta be given, you can find out x and y, and then you can plug that into x and y here. Yeah, instead of dealing with all these functions as functions. So you could similarly find the partial of f with respect to theta by doing the same thing. But we're not going to do that. All right. I made up a worksheet. I don't know if we should do them. We don't have to do posters or anything that fancy. And in fact, these worksheets or these problems would be more like from last section's problems. So why don't I hand them out and have you guys work on it together and see how you can do.